In this video, we will discuss how to draw the electron pushing arrows for an acid-base step. Then in the next video in this series, we will show how to draw an SN1 mechanism that includes an acid-base step. This is important material because most SN1 mechanisms include an acid-base step. And in fact, the material in this video is crucial to your Ochem success because most mechanisms in organic chemistry involve acid-base steps. You can't succeed in organic chemistry unless you've mastered the material in this video about how to draw the electron pushing arrows for an acid-base step. Now, we've talked about various roles in organic chemistry. What are the three roles that we've discussed so far that atoms can play in mechanisms? I hope you're answering each question that I ask. Well, the answer to that is we've discussed the roles of nucleophile, electrophile, and leaving group. We've discussed the roles of nucleophile, electrophile, and leaving group. I hope you've mastered the material here on the screen. Now we're going to have to discuss two new roles. What are the new roles that we're going to have to discuss? Well, acid and base. Please pause the video and give a precise definition of the role base. We're able to do that? A lot of students have difficulty with that. Well, one thing you should have known is that a base is something that takes a proton. The definition you learned for base in general chemistry is that a base takes a proton. It takes the proton from who? From the acid. A base is something that takes a proton from an acid. What would be a good symbol for proton? What's a good symbol for proton? Well, I hope you're familiar with the idea that we can use the symbol H+ to stand for a proton. H+ stands for a proton. This is a good symbol because it emphasizes the formal charge on a proton. Remember, the most important factor to keep focusing on is the formal charge. The most important thing about a proton is that it has a positive formal charge. So a base takes a proton from an acid. But when we defined nucleophiles and electrophiles and leaving groups, we used two-part definitions. We also focused on what each role did with electrons. So what does a base do with electrons? Donate or receive electrons. A lot of students don't know this, but the answer is that a base donates electrons. So here we have a two-part definition. The base donates electrons to take a proton from an acid. Now, this two-part definition should make sense to you. Notice that we're doing the opposite thing with the electrons and the protons. The base is taking a proton, but it's donating electrons. Taking is the opposite of donating. Well, that shouldn't surprise you because focus on the charges. We know that the charge on an electron is negative. An electron has an opposite charge from a proton. Since an electron has an opposite charge from a proton, it should make sense that the thing that the base does with the proton is the opposite of what it does with an electron. So as usual, focusing on the charges is the key to thinking clearly about Ochem. Most students do not have a very clear definition of the term base in their minds, so it's really important that you pause and memorize this definition for a base. This is the most useful definition of the term base in organic chemistry. In organic chemistry, it's most useful to think of a base as something that donates electrons to take a proton from an acid. Now, this should remind you of the definition of a nucleophile. We know that a nucleophile also donates electrons. If a base donates electrons and a nucleophile donates electrons, what's the difference? Well, remember, a nucleophile is donating electrons to join the electrophile, whereas the base is donating electrons to take a proton. Now you can see why we need a two-part definition, so we can see how a base and a nucleophile are similar, but also how we can see how they're different. Well, let's move on now to the term acid. Pause the video and try to come up with a precise definition for the term acid. Well, that should have been easy if you model your definition of an acid on our definition of a base. Obviously, an acid is the opposite of a base. So where the base donates electrons, the acid will be receiving electrons. And where the base takes a proton, the acid will be giving a proton. And who does the acid give the proton to? To the base. Again, we have a two-part definition. The acid receives electrons to give a proton to a base. You can see that an acid is somewhat similar to an electrophile and to a leaving group, because all three of those receive electrons. Acids, electrophiles, and leaving groups receive electrons. So we need a two-part definition so we can see how those three roles are different from each other. They all receive electrons, but an electrophile receives electrons to join a nucleophile. A leaving group receives electrons to leave an atom, and an acid receives electrons to give a proton to a base. So we can see how an acid is similar to, but also different from an electrophile and a leaving group using these two-part definitions. It's crucial that you have all 5 of these two-part definitions memorized. These are the most useful definitions of these 5 roles in organic chemistry. So now we've introduced the 5 main roles in organic chemistry. The 5 main roles in organic chemistry are nucleophile, electrophile, leaving group, acid, and base. You need to have mastery of those roles to succeed in organic chemistry. Obviously, there are other less important roles such as solvent or spectator ion, but these are the 5 most important roles in organic chemistry. Unfortunately, most students don't have a very clear idea in their heads of what exactly a base and an acid is. So now would be a good time to pause the video and really memorize these definitions. I hope you did that. Now, previously when we talked about roles, we discussed how to draw the electron-pushing arrows for a nucleophile, an electrophile, and a leaving group. Well, we have to learn how to do that for an acid and base as well, because remember, our whole goal in this video is to learn how to draw the electron-pushing arrows for an acid-base step. So pause the video and see if you can draw the correct electron-pushing arrows for a base. Did you really try to draw the correct electron-pushing arrows for a base? Most students have a hard time with that, but let's talk about that. So let's say we have a base. Remember, we know the base is going to donate electrons. So should the electron-pushing arrow point towards the base or away from the base? It should have been obvious to you that the electron-pushing arrow is going to point away from the base because the base is donating the electrons. That means that the base goes at the tail of the electron-pushing arrow. Remember, this is how we would label the head and the tail of an electron-pushing arrow. But who should go here? Who goes here? Again, do you have an answer? What goes here? Well, remember that the base is donating electrons to take a proton from an acid. So here we put the hydrogen that the base is going to be taking. At the head of this arrow, we put the hydrogen that the base is going to be taking. And of course, what's the hydrogen attached to? The acid. Because remember, the base is taking the proton from the acid. So this is a good way to draw the electron-pushing arrow for a base. The arrow goes from the base to the proton attached to the acid. In a way, this should seem very simple and straightforward, but my experience is that most students have a really hard time drawing this electron-pushing arrow. So make sure you understand why this is the correct electron-pushing arrow for a base. Well, to continue, now you have to draw the electron-pushing arrow for an acid. Pause the video. How would you draw the electron-pushing arrow for an acid? Well, the acid needs to receive electrons. So the acid should go at the head of an electron-pushing arrow, and it's receiving electrons to lose a proton. So do you see this is the logical electron-pushing arrow for the acid. The head of the arrow is on the acid, showing that the acid is receiving electrons. And the tail of the arrow is on the bond between the acid and the proton, the hydrogen, showing that the acid is going to break its bond. The acid will be breaking its bond with the hydrogen. That's what it means to give up the hydrogen to the base. So this is what the electron pushing arrows look like for an acid-base step. Remember, that's our main goal for this video, to learn what the electron pushing arrows look like for an acid-base step. The base is donating electrons to take this proton, and the acid is receiving electrons to lose that proton. All right, as I said, most students have a really hard time drawing the correct electron pushing arrows for an acid-base step. Let me show you some common mistakes that students make so you can watch out for that. Here is a common student mistake. Commonly, students draw the arrows like this. Oftentimes, students will draw the arrows like this because they think, oh, the proton is moving towards the base. Since the proton is moving towards the base, let me show this more clearly by writing it like this. This would be the mistake. Here's the mistake. This is tempting because we know that the proton should be moving towards the base. But the reason this is wrong is, remember, this is not called a proton pushing arrow. It's called an electron pushing arrow. The purpose of this arrow is not to show the movement of the proton. The purpose of the arrow is to show the movement of the electrons. So it's tempting to draw the arrow this way to show the movement of the proton, but that's wrong. Instead, we should show the arrow this way to show the movement of the electrons. So watch out for this mistake. Don't draw an arrow to show the movement of the proton. That's a mistake. Instead, draw your arrow to show the movement of the electrons. And now I can show you another common mistake. Another common mistake is to draw the arrow like this and to have the base attack the acid directly. You can see this is wrong because the base is not supposed to attack the acid directly. It's supposed to take a proton from the acid. That's why this arrow is correct and this arrow is wrong. But this is very tempting because this would be the correct arrow for a nucleophile electrophile step. This is what the arrow would look like for a nucleophile electrophile step. So it's tempting to get that confused with an acid-base step. So in a nucleophile electrophile step, you might draw an arrow like this, but for an acid-base step, don't draw the base attacking the acid directly. Instead, draw the base attacking the proton on the acid. So partly because of those two common mistakes, students have a really hard time drawing the correct arrows for acid-base steps. It's crucial to understand the similarities and differences between a base and a nucleophile. Why do I say that a base is similar to a nucleophile? How is a base similar to a nucleophile? Remember that each time I ask a question, I really hope that you're pausing the video and coming up with an answer. Did you answer this? The answer is that both a base and a nucleophile donate electrons. A base and a nucleophile both donate electrons. That's how they're similar. Well, there must be some way that they're different. How is a base different from a nucleophile? Here's the answer. A nucleophile donates electrons to join an electrophile, whereas a base donates electrons to take a proton from an acid. So here's how a base is different from a nucleophile. To succeed in organic chemistry, you need to be very clear about how bases and nucleophiles are similar and also how they're different. So you should pause the video and carefully study these ideas. I've mentioned that students have a really hard time drawing the electron pushing arrows for an acid-base step. And a good way to think about it is if you forget what a base is, remind yourself that it's similar to a nucleophile. If you forget what a base is, remind yourself that it's similar to a nucleophile. It's similar in that they both donate electrons, but it's different in that the base is taking a proton rather than joining an electrophile. So again, that's how you can remind yourself what a base is if you forget it. Remember that it's similar to a nucleophile in that they both donate electrons, but different in that the nucleophile takes a proton, whereas the nucleophile joins the electrophile. Because students have so much trouble drawing the electron pushing arrows for an acid-base step, you might find it helpful to memorize this slogan. The first arrow for an acid-base step points from the base towards the proton. From the base towards the proton. Of course, you shouldn't have to memorize this. You should be able to figure it out. Since a base donates electrons, it should make sense that the arrow points away from the base. And since the base is taking a proton, it should make sense that the arrow points towards the proton. You should be able to figure this out from the definition. But to save time and allow you to get through mechanisms more smoothly, it might also be a good idea to memorize this slogan because it gives students so much trouble. So perhaps you should pause the video and memorize this slogan. If you can draw the first arrow for the mechanism correctly, I think once you've drawn this arrow, it shouldn't be too hard to figure out this arrow, because the acid has to lose the proton. The part that really gives students difficulty, I think, is drawing this first arrow. Because again, oftentimes students draw the arrow incorrectly like this, or oftentimes students draw the arrow incorrectly like this. Those were both wrong, so instead you might want to memorize what the correct way to draw the first arrow is. Now, you might wonder, if we say that the base takes an H+, why is the hydrogen drawn with 0 formal charge in this picture? Well, the hydrogen does have neutral formal charge while it's attached to the acid, but notice that when the base takes the hydrogen will be leaving its electrons behind with the acid. The electrons for this hydrogen are in its covalent bond with the acid, and this arrow shows us that when the base takes the hydrogen will be leaving its electrons behind with the acid. So, the hydrogen is drawn with neutral formal charge in this picture, but when the base takes the hydrogen, it will be as if the base was taking an H+, and the base will become one step more positive after taking this hydrogen. The base will become one step more positive after taking this hydrogen, so it's appropriate to say that the base is taking an H+, even though the hydrogen is drawn as neutral in this picture. Well, now that we've learned how to draw the electron-pushing arrows for an acid-base step, the next step is we have to learn the clues that tell us when an atom will play the role of an acid and when an atom will play the role of a base. What do you think would be some good clues that an atom could play the role of base? Well, it turns out that the clues for bases are basically the same as the clues for nucleophiles. That shouldn't surprise us. Remember that bases are similar to nucleophiles because they both donate electrons. So the clues for a base are the same as the clues for a nucleophile. So what would those clues be? Well, I hope the first clue you focused on was the formal charge. The best clue for a base is also the best clue for a nucleophile, a negative formal charge. That should make sense. A negative formal charge makes you want to donate electrons to get rid of your negative formal charge. Remember, electrons have a negative charge. But what do you do if none of the starting materials has a negative formal charge, or if the atoms with the negative formal charges are not great bases? What's another clue for a base? Well, the same as the clue for a nucleophile. Remember, when can we use a neutral atom as a nucleophile? Well, we can use neutral atoms with lone pairs as nucleophiles, and the same is true for a base. We can use a neutral atom with a lone pair as a base. That will generally be neutral oxygen, although occasionally you might also use neutral nitrogen as a base. For example, water and alcohols both have neutral oxygens with lone pairs. So both water and alcohols can be used as bases. And in fact, in this video series, we're usually going to be using water or alcohol as bases. You should know what an alcohol is. You should know that an alcohol is an OH group connected to a carbon chain. Atoms with negative formal charges can be bases, but we're actually not going to use those much in this video series. In this SN1 video series, we're usually going to be using water and alcohol as our bases. Those have neutral oxygens that have lone pairs. Now, what's the clue for when an atom can act as an acid? Well, focus first on the formal charge. Remember, an acid is something that wants to receive electrons. So what would make you want to receive electrons? I hope you said a positive formal charge. An atom with a positive formal charge is likely to be a good acid because the positive formal charge makes the atom want to receive electrons. Now, of course, there's another obvious requirement for being an acid. In order to be an acid, you have to be attached to a hydrogen, right? Remember, the whole definition of an acid is something that can give up its hydrogen. An acid has to be able to give up its H+. It can only do that if it has an H. You can see here that to be an acid, you have to be connected to an H. So the clue here is that you have to have a positive formal charge and be attached to a hydrogen that you could give up to the base. So in this video series, we will usually use water or alcohol as our base, and we'll usually use an atom with a positive formal charge as our acid. Now is a good time to pause the video and learn these important clues. Okay, here's a problem for us to try. Notice the instructions. We're not going to be drawing an SN1 or SN2 mechanism here. We're just going to be drawing a single acid-base step. So please pause the video and try to draw the mechanism and product for a single acid-base step. I hope you actually tried that. Let's work on this together. This is a really crucial skill for your Ochem success. Well, it would be a good idea to start by numbering our carbons. Then we can try to identify the roles that atoms will play. Well, we should certainly start by focusing on the formal charge. When we see this oxygen with a positive formal charge, we expect this oxygen to be our acid. So I'll label this A for acid. Remember, a positive charge and an attached hydrogen makes you acidic. How do I know this won't play a different role like leaving group? Well, because the problem said this is an acid-base step, not a nucleophile electrophile step. Now, what's the other role? We shouldn't be looking for a nucleophile here. We need to look for a base. Well, there's nobody here with a negative formal charge, but we've learned that we can use water as our base. So I'm going to label the oxygen in the water as the base, because the oxygen is a neutral atom with a lone pair. Used the clues that we just learned up here. The positive formal charge indicates that this oxygen is acidic. And this neutral oxygen in water we treat as the base. Notice, as usual, how crucial the formal charges are. With a positive formal charge, we expect that this oxygen will be the acid. Since this oxygen is neutral, it's less likely to be the acid, and in this case, we use it as the base. So there's a big difference here between the positive oxygen and the neutral oxygen. The most important factor in Ochem is the formal charges. Now comes the really tricky part for most students, drawing the electron pushing arrows. Most students have a real hard time drawing the electron pushing arrows. I hope it wasn't too hard for you, though. Remember, we've learned how to do that. Remember, we kind of memorized what the first arrow looks like for an acid-base step. We memorized that the first arrow points from the base towards the proton. So the arrow will start over here and point to one of these protons connected to the oxygen. Now, because this is written as H2, it's not really considered correct to draw this arrow. You have to, you can't have a group of hydrogens participating in the reaction. So what we actually have to do here is separate the hydrogens. Take your time, separate the hydrogens, and draw the bond to one of the hydrogens. So that's our first arrow, from the base towards the proton. That should make sense because remember, a base is an electron donor. This shows the base donating its electrons to the proton. And now we need a second arrow for the acid. That should be easy because we would expect that electrons would be moving towards this positive charge. So here's our second arrow for the acid. Now you can see why we had to draw this hydrogen separately so we could draw this bond. This is not a good way to draw it. This is not a good way to draw it because we haven't shown which of the hydrogens we're attacking. You have to separate the two hydrogens. And this is still not acceptable. This is still not acceptable because we haven't shown the second arrow. This is still not acceptable. This is still not acceptable because we haven't drawn the bond that the arrow is taking the electrons from. You have to draw something like this. You have to separate the hydrogens, and you have to actually draw the bond to one of the hydrogens so you can correctly show this arrow. This would not be considered acceptable. And this would certainly not be considered acceptable. And this is certainly not acceptable. suppose some professors are more picky about drawing the arrows exactly correctly than others. Professors themselves are sometimes a little bit careless about drawing acid-base arrows. But as a beginning Ochem student, try to draw the arrows like this, because that might be important for getting full credit, and because also that will allow you to understand the mechanism better. Here's another common wrong way to draw the arrow. This is clearly wrong because the arrow is going in the wrong direction, but this is very tempting. This is a tempting mistake. Students draw this arrow because they say that the proton is moving towards the water. And in a way that's true, but remember, it's not the purpose of this arrow to show the movement of the proton. The purpose of the arrow is to show the movement of the electrons. It's an electron pushing arrow, not a proton moving arrow. So this arrow is tempting, but wrong. And here's another arrow that's tempting, but wrong. It's tempting for the oxygen to directly attack the oxygen with the positive formal charge. It's tempting to draw an arrow like this. This is wrong because this looks like a nucleophile-electrophile arrow. This might be, this is an arrow that's close, I guess, to being something you might draw in a nucleophile-electrophile reaction. But remember, a base is supposed to take a proton. So the arrow from the base has to point to the proton, not to the atom with the positive formal charge. So this is another common wrong way to draw the mechanism for an acid-base step. Now we can draw the products from this step using this approach. Let's look at this arrow. Does this arrow tell us to erase a bond, draw a bond, or both? I hope it's intuitive that this arrow tells us to draw a bond. Between which two atoms? Between this oxygen and this hydrogen. That should be obvious because the arrow goes from the oxygen to the hydrogen. So this arrow tells us to draw a bond between this oxygen and that hydrogen. Here I've drawn that bond between this oxygen and this hydrogen. Now remember, the most important thing to get right is the charges. Because this is the first arrow, we have to change a charge. We change the charge on the atom at the beginning of the series of arrows, which is this oxygen. This oxygen started neutral, and it's losing electrons. So it should become one step less negative, which means one step more positive. So this oxygen ends up with a positive formal charge. It's crucial to include that positive formal charge. The oxygen started neutral and lost electrons, so it became one step more positive. We discussed in the last video that the most common student mistake when drawing the products is forgetting to change the charge at the beginning of the series of arrows. So take that seriously and make sure you change this first charge. Now we can move on to this arrow. Does this arrow tell us to erase a bond, draw a bond, or both? I hope it's intuitive that this arrow tells us to erase the bond between the oxygen and this hydrogen. Now I've shown that I've erased the bond between this oxygen and this hydrogen. And again, we have to change a charge. We change the charge on the atom at the end of the series of arrows. This oxygen started positive and it gained electrons. So it should become one step more negative. That means one step less positive. When it gains electrons, this oxygen changes from positive to neutral. In fact, I've already changed its charge here to neutral. Remember, you always change two charges at the beginning and end of the series of arrows. We never change the charge on the atom in the middle of the series of arrows. We always change the charge at the beginning of the series of arrows and at the end of the series of arrows. The most common mistake is forgetting to change the charge on this atom at the beginning of the series of arrows. Well, the instructions were just to draw the mechanism for a single acid-base step, so we can stop here. By the way, there's another acceptable way to draw this product. You could also draw this product like so. It's no longer necessary to draw the hydrogen separately, so you could draw this as H3O+. This is also okay. This does not let you show the new bond, but eventually I think you'll find that this is a helpful shortcut to draw the product like this rather than like this. On the other hand, drawing this product would be a huge mistake. The most important part to get right is the formal charge. If you leave out the positive formal charge, your answer is mistaken. You have to include this positive formal charge on the oxygen. I guess I'll go ahead and write this product like this because this is the standard way that we're going to write it to save time in the rest of this video series. Were you able to get this right? The goal is that this problem should have been boringly easy. This was supposed to be a boringly easy problem. My experience is that most beginning students find this pretty challenging. Most beginning students have a lot of trouble drawing the arrows for an acid-base step. So you need to keep practicing until it's boringly easy for you to draw the arrows for an acid-base step. Most mechanisms on most problems for the remainder of your Ochem class will involve acid-base steps. So it has to be boringly easy for you to draw these mechanisms and to draw the correct products from those mechanisms. Next problem, please pause the video and try this problem. I hope you're actually trying these problems on paper. Now we can go through this together. We can start by numbering all the carbons. Whoops. Notice that I'm actually numbering all the carbons, both the carbons in bond line notation and the carbons in condensed notation. That's a good habit for a beginning student. Now we need to identify roles. We're not ready to draw the electron pushing arrows until we've identified roles. We should focus first on the atom with the formal charge, because if it's positive formal charge, we expect this oxygen to be our acid. Now we look for a base. We might look first for a negative formal charge, but there are no atoms with negative formal charges. So now we look for a neutral atom with a lone pair. And here we have an alcohol, which has a neutral oxygen with a lone pair. We've specifically memorized that neutral alcohols are commonly used as bases. So I'll label this as the basic atom. Only now that we have written down the roles, only now should we write down the electron pushing arrows. This is a step that's tricky for many students. Have you memorized this idea? The first arrow points from the base towards the proton. From the base towards the proton. Now, in order to deal with this, we're going to have to draw the hydrogen extending out from a bond. The first arrow goes from the base towards the proton. That makes sense because a base is an electron donor. It donates electrons to take a proton. So this is a logical arrow for a base. And then the second arrow for the acid should be easy. It's going to point from the bond towards the atom with the positive charge. Here's the general pattern we learned earlier for the electron pushing arrows for an acid-base step, and you can see how these arrows match this pattern from the base to the proton, and then from the bond with the proton to the acidic atom. I hope it was boringly easy for you to draw that electron pushing arrow. Now we can draw the products from this step. This arrow tells us to form a bond between the oxygen and that hydrogen. And the standard way to show that is just to change this from an OH to an OH2. And that when we draw this as an OH2, that implies that there's a new bond to a new hydrogen. It's probably not necessary to actually specifically draw that new bond. Now here's the most important thing, to change the charge. This oxygen is at the beginning of the series of arrows. It started neutral and it's losing electrons, so it should become one step more positive. Remember, the most common student mistake is forgetting to change the charge at the beginning of the series of arrows. But without this positive charge, your answer is wrong. Now, this arrow tells us to break the bond between this oxygen and this hydrogen. I forgot to number. This is carbon 1, 2, 3, 4, 5, 6, and 7. Make sure that your numbers are consistent with your numbers for the starting material. And again, change a charge. This oxygen started positive and it gained electrons, so the oxygen becomes neutral. And clearly we've shown that we've broken the bond between this oxygen and this hydrogen. Okay, so we're done. That's the mechanism and the product for this acid-base step. I hope that that was a boringly easy problem for you. Remember, most mechanisms for the remainder of the course will have acid-base steps, so the acid-base steps have to be boringly easy for you. make sure you have memorized this pattern for the arrows for an acid-base step, and particularly focus on memorizing how to draw the first arrow for the acid-base step, because that's the one that, if you can get that one right, you can probably get the rest of the mechanism correct. You can compare these, our last two examples. Notice that in our first example, I drew the acid on the left and the base on the right. And in this example, I drew the base on the left and the acid on the right. But it should be obvious that it doesn't really matter who's on the left and who's on the right. What matters is who is the acid and who is the base. So make sure that you start by labeling the roles that the atoms will play, and only then draw the electron pushing arrows. Notice how crucial the formal charges are. We used the oxygen with the positive formal charge as the acid, and we used another neutral oxygen as the base. We talked earlier about how oftentimes we're going to use water and alcohols as bases in this video series. So here's an example with water as a base, and here's an example with an alcohol as a base. Please pause the video and try this problem. Now we'll discuss, well, what is our most important tool for checking if the electron pushing arrows are reasonable? The most important tool for checking the electron pushing arrows is the formal charges. So let's focus on this oxygen with the positive formal charge. Is it reasonable to put a positive formal charge at the beginning of the series of arrows? I hope you said no. It doesn't make sense to put a positive charge at the beginning of the series of arrows. Since this oxygen is positive, it wants to gain electrons, not lose electrons. Always keep in mind that an electron has a negative charge. Well, if you're positive, you would want to gain negative electrons. You wouldn't want to lose negative electrons. These arrows are not reasonable. The O plus wants to gain electrons, not lose electrons. So the O plus belongs at the end of the series of arrows, not at the beginning of the series of arrows. You can see that these electron-pushing arrows violate this pattern that we've established. We've said that at the beginning of a series of arrows, we should always put an atom that's negative or neutral, never an atom that's positive. And we violated that here. This is the rule that we violated. We should never have a positive atom at the beginning of the series of arrows. These arrows are unreasonable because they do place the positive atom at the beginning of the series of arrows. Now, these arrows are tempting for students because we do have a lone pair at the beginning. Students think that maybe this oxygen should go at the beginning because it does have a lone pair. Well, it's true. This oxygen does have a lone pair, but not everything with a lone pair is an electron donor. Negative atoms with a lone pair are electron donors because they want to get rid of electrons. And neutral atoms with a lone pair can also be an electron donor. But we would never have an atom with a positive formal charge as an electron donor, even if it has a lone pair. Atoms with positive formal charges want to receive electrons, even if they have lone pairs. The most important tool for drawing the correct electron-pushing arrows is the formal charges. Don't put an atom with a positive formal charge at the beginning of the series of arrows, even if it has a lone pair. Compare these bad arrows with the correct arrows that we already drew when we were solving the previous problem. These are good arrows because these arrows end on the atom with the positive formal charge. It's good for arrows to end on the atom with the positive formal charge. These are bad arrows because these arrows begin on the atom with the positive formal charge. You should never put an atom with a positive formal charge at the beginning of the series of arrows. Notice that these good arrows are consistent with all of these patterns. We want to put an atom that's negative or neutral at the beginning of the series of arrows. Well, with these good arrows, we have a neutral atom at the beginning of the series of arrows. We want to put an atom that's neutral in the middle of the series of arrows. Well, here we do have a neutral hydrogen in the middle of the series of arrows. And we want to put an atom that's positive or neutral at the end of the series of arrows. Well, here we do have this oxygen, which is positive at the end of the series of arrows. Now, before we finish this, this video, there's a few other details that would be useful to understand about acid-base reactions before we start applying this to SN1 reactions. We need to understand that there's a difference between strong bases and weak bases. A strong base, well, remember that a base is something that wants to take a proton. A strong base is something that is very eager to take a proton, whereas a weak base is something that is less eager to take a proton. So water and alcohols would be classified as weak bases. Water and alcohols are weak bases. Neutral water and neutral alcohol are weak bases. They can take a proton, but they're less eager to take a proton than a strong base would be. So you should know that these are weak bases. On the other hand, we can also talk about strong acids and weak acids. A strong, well, remember, an acid is something that wants to give a proton away. A strong acid is something that's very eager to give away a proton. A weak acid is something that is less eager to give away a proton. Atoms with positive formal charges can generally be referred to as strong acids. Atoms with positive formal charges and an attached hydrogen are generally strong acids. That is, an atom with a positive formal charge is usually very eager to give away a proton. Another way to think about it is strong means reactive, and weak means less reactive. So a strong acid is very reactive, very eager to give away a proton. A weak base is not that reactive. It can take a proton, but it's not that eager to do so. Let's consider when you combine various types of acids and bases. Sometimes an acid-base step can occur, but sometimes the starting materials are not reactive enough for an acid-base step to occur. So do you think that a strong acid can react with a strong base? I hope you said yes. Remember, strong means reactive. These are both reactive, so here we would have an acid-base step. I'll make a check mark here to show that yes, in this case, an acid-base step can occur. How about if we have a strong acid and a weak base? Well, the weak base is not very reactive, but the strong acid is, and as a result, yes, an acid-base step can occur. We don't need both things to be strong. It's good enough for one of the starting materials to be strong. So by that same token, a weak acid and a strong base, again, yes, an acid-base step can occur. The acid here is not very reactive, but the base is reactive, so that's good enough for an acid-base step to occur. But if you have a weak acid and a weak base, I'll put an X to show that you generally would not get an acid-base step here. If both the acid and the base are weak, if they're both fairly unreactive, then we don't expect to get a acid-base reaction. So the general rule is that at least one of these two starting materials should be classified as strong. If you have both a weak acid and a weak base, we generally expect that we would not get an acid-base step. These are not perfectly reliable rules. There are some exceptions to this, but this is a useful pattern that will help you on many Ochem problems. This is a general pattern that's helpful on many Ochem problems. There are some exceptions. So we better go back and make sure that those examples that we did previously really make sense. Earlier we said that this positive oxygen is an acid. Is it strong or weak? Well, because of the positive formal charge, we expect this to be a strong acid. On the other hand, we've memorized that neutral water is a weak base. Well, it's good. In this case, this is good enough. We can get a reaction. Strong acid plus weak base, we can get a reaction. They don't both need to be strong. Only one of them needs to be strong. So yes, this was a reasonable reaction. Let's check this example. We said earlier that this is a base. Is it strong or weak? Well, this is a neutral alcohol, and we've memorized that neutral alcohols are weak bases. On the other hand, this compound has a positive formal charge, which makes it a strong acid. Well, we know it's good enough if one of the starting materials is strong. So yes, this is a reasonable acid-base reaction because one of the starting materials is strongly reactive. So this reaction did make sense. So I've encouraged you to always label the roles for acid-base steps. And in fact, from now on, I encourage you to get into the habit of labeling whether each acid or base is strong or weak. It's important in Ochem to distinguish between strong and weak acids and bases. Get into the habit when you label acids and bases to label them as strong or weak. If you have both a weak base and a weak acid, you're probably trying to do a reaction that doesn't really make sense. Usually weak acids don't react with weak bases. Now, one more detail we have to deal with is Cl minus, Br minus, and I minus. Now, we would expect these to be bases because of their negative formal charges. And they are basic. However, they are very weak bases. Cl minus, Br minus, and I minus are very weak bases. Despite their negative charges, Cl minus, Br minus, and I minus are very weak bases, even weaker than neutral water. Neutral water is a better base than Cl minus, Br minus, and I minus. Why is that? Well, you should know that these are very strong acids. You should recognize that HCl, HBr, and HI are very strong acids. But you should also know that the conjugate of a very strong acid is a very weak base. And these ions are the conjugates of these very strong acids. So because these compounds are very strong acids, and because these ions are the conjugates of those very strong acids, these ions are very weak bases, even weaker bases than water or alcohol. The upshot is that most professors would prefer that you should not use these ions as bases unless there's nothing else better around. Most professors will only use these species as bases if there's nothing else better around. In particular, most professors would prefer for you to use water and alcohol as the base, rather than Cl minus, Br minus, or I minus. The upshot is that if water or alcohol is the solvent, most professors would prefer for you to use the water or alcohol as the base, instead of Cl minus, Br minus, or I minus. Also, because alcohol and water are the solvent, you don't need to worry about running out of them. So even if you've already used water or alcohol earlier in the mechanism, it's okay to use them again as the base. We don't worry about running out of water or alcohol because they're the solvent. And the solvent is a starting material that is generally going to be present in far excess of the other starting materials. There's way more of the solvent than the other starting materials, so we don't need to worry about running out of the solvent molecules, even if we've already used them earlier in the reaction. One final note is that neutral chlorine, bromine, and iodine are not basic, even though they have lone pairs. These have lone pairs, but they're not basic. That shouldn't be surprising. If chlorine, bromine, and iodide are very weak bases, even with a negative charge, it's not surprising that they're not really basic at all when they're neutral. That would make them even less willing to donate their electrons. So we're not going to use neutral chlorine, bromine, or iodide as bases. We know, what do we use these for? We use neutral chlorine, bromine, and iodide as leaving groups. What do we use negative chlorine, bromine, and iodide for? We're rarely going to use them as bases, but we know that we commonly use negative chlorine, negative bromine, and negative iodine as good nucleophiles. These ions are very weak bases, but we've learned earlier that they are good nucleophiles. You can see that all these different patterns for nucleophiles, electrophiles, leaving groups, acids, and bases, these patterns are getting pretty complicated. Well, unfortunately, this is just a difficult, complicated class. You can see why Ochem is considered a tough class. It's because there's a lot of complicated patterns to learn. So here we have a summary of some of the patterns that are useful to understand for acids and bases. There are certainly other things to learn about acids and bases, but these are some clues and ideas about acids and bases that will be useful in this video series on SN1 reactions. In the next video, we will learn how to include an acid-base step in an SN1 mechanism.